Welcome to episode number 6. Today, I wanted to talk about important concepts that people talk about a lot, which is explainability and bias, and talk about how we deal with that in the DAISY world and how we see that evolving. I think these topics are very important because to really aid in the adoption of AI, we need to build trust. I think it's adoption of technology, not just AI, any technology is about building trust in the people who use the technology. I think having something that's understandable, that is transparent, explainability and bias are about transparency, right? And so creating transparency will then create the trust that there's nothing untoward happening with the technology, that it's working fairly, properly, that we all understand what it's doing. And I think that's the first element. And so if you read in Daisy's white papers, we see a trust journey is one of the important elements of change management, to build that trust over time and stages with people who use the technology. Much of machine learning is a data-driven approach. And because you're assembling data and you're finding patterns in data with complex algorithms, explainability becomes very difficult. And many machine learning algorithms are a black box and need a separate step from developing the patterns and finding the patterns, whether you're doing deep learning or even linear regression, you're finding some mathematical equation that fits the data well. And then as a separate step, I think you then have to explain why are these patterns exist? What is the content in those patterns? And so that can be a challenge, the more complex that a mathematical model is. And even a simple model like linear regression, if you had that income is equal to a constant plus 1.5 times age plus 3.7 times educational level, even though you had age and educational level in that, are those variables the causal variables? There's not necessarily true that the features and the data that shows up in a model explains causality, because we know there are many spurious causations out there. And there's probably a website that you can look at that has kind of humorous causations. And one that jumps to mind is that, the murder rate is correlated to ice cream sales. So yes, there's a correlation there, but that's not causal. There's an indirect causality because ice cream sales are higher in the summertime. They say when the weather is warmer, more people are out and about and are interacting, and that causes increase in murder rates. So it's more complex. So causality is important. So even though you have a feature in a model, that doesn't mean it explains the model. So explainability is a separate step, and it's very difficult in black box, purely data-driven machine learning approaches. And so in earlier episodes, we talked about DAISY building causal theories, and I think that's the scientific method. And I think one of the benefits of having a theoretical approach where you come up with a mathematical theory is that it's based on a number of what I would call fundamental truths, or attempts to create fundamental truths that explain the dynamics of business. And so if I was to look at an insurance example, our fundamental theory in insurance is that if you are different than the norm, then that's likely to be fraud or risk or something that you can't pay or automate, right? And so the theory is different than the norm. Sounds very simple. Different than the norm implies that you can compare entities. So let's say talk about comparing people, we'd say, okay, amongst similar people, well, what does that mean? People who are of the same age, who maybe live in the same area of the world, live in the same city, and they're in an urban setting, people who are the same gender, who have the same ethnic background, who maybe have the same education, who maybe have a similar career, who live a similar lifestyle. Okay, so that's very complex, comparing people to say these people are peers, they're similar people. So that's first, there's a comparison of similarity. And, we can group people using non-biased facts, just that are attributes of people and great peer groups of people. And then we can say, well, all these people that are in the same group, who are the outliers in that group, outlying behavior? So our theory in insurance is that if you have outlying behavior compared to your peers, then that's likely indicative of fraud or high risk or inability to automatically pay claims. So then we look at behavior. What do you have to define what the behavior of the people is? And this would be all the behavior associated with claims. So what do your claims look like? What are the attributes of your insurance claim? Is this claim larger than normal? This is a car accident. Is that car accident, was it, I'm comparing also not only you as the individual, I'm comparing now the accident to all its peers. It was a certain vehicle, certain time of year, certain geographic area, certain characteristics of incident. And now look at the claim. So this is a low speed accident, happened in the wintertime in Toronto in December. And now we look at the characteristics of low speed accidents. Is the dollar amount consistent with other ones? Is the ratio of bodily injury? Did the driver have more injuries than similar accidents? Is the type of damage consistent with that? And you can calculate multiple attributes. Is the time since the beginning that the policy just started yesterday, or is this policy 3 months old? So duration of the policy, sometimes, the earlier in the life of a policy, that could be an outlier. If you just got a policy, is it a rental car? Did you just rent the car at the airport 2 hours ago? Is it fully loaded with all kinds of insurance so that you could maximize the benefit? So you look at all the attributes of the claim and the nature of the policy, and then you compare it to all the peers and you say, is that different than the peer? And this way, it's not profiling. I know we are concerned when we look at, law enforcement perhaps profiling certain peer groups, right? Certain ethnicities. This is now a way to overcome profiling, in that within any peer group or any ethnic group, the idea is to find the outliers or the bad apples or the different apples. So it's not profiling. It's actually eliminating the issue of profiling, because I'm finding different attributes or different behaviors in a group of people or claims or events that are similar, and I'm finding things that behave differently compared to all their peers. And that's a key element of theory. So that's explainability. So now, if I find a claim, now I can explain it to the users, to the fraud investigators or the underwriters or the adjusters who review the claim. We can say, this claim is similar to all these other claims, and here's all the similar facts. And the people associated with the claim, here's all the similar people. And here are all the things that are different about this claim when I compare it to those two pools of people, claim type, event type, and peer. And now I can have an explanation to say, this is why it's different. And so that's the explainability in our theory of insurance risk or theory of risk management, is to first explain why it's a peer. What are the peers? Who are the peers? What are the attributes of the peers? Convince the person looking at it that, yes, indeed, that is the similar claim. And then looking at what is different about it. What is behaviorally different about this claim or event than everyone else? And mathematics says that if I have 1,000 attributes, 1,000 behavioral attributes about a claim, which I can derive all kinds of metrics about a claim. There could be 10 or 15 numerical features about a claim. I can then derive many by looking at ratios, polynomials, calculations about that, averages, variations, all of those things. So if I have 1,000 independent features, so independent variables about a claim that describe its behavior, and each of those variables is completely independent, so it's not related or correlated to other features. And if, let's say, any one of those features has a 99% chance of being wrong in and of itself, if I say the dollar amount of this claim is different than its peers, that's 99% wrong. If I just made the decision on one feature alone, that would be wrong 99% of the time. Well, the mathematics says that if I have 1,000 features, 0.99 to the power of 1,000 equals 4 times 10 to the minus 5. So that's 0.00004. So 1,000 independent features that are each of them 99% wrong. When you combine them all together and say, these 1,000 features, when I look at them as being outliers, I have a 99.99996% probability of being right. So that's the idea of and the explainability behind it. And then further, the type of mathematics that Daisy uses is fuzzy logic, where we can translate mathematical descriptions into an English language statement. So we can say that because there's a fuzzy score of 0.9 of 999 out of 1,000, let's say that means it's an outlier. Zero is not an outlier. 1,000 is a total outlier. This has a score of 999 because this particular individual and this claim is larger than 98% of all other similar claims. And it happened one day after the policy was instantiated, which is different than 96% of all claims. And so you can combine those 1,000 variables into 1,000 English language descriptions that explain exactly why we think that's an outlier. So that's a way of doing explainability. And we don't have to do all 1,000 features because all 1,000 things won't necessarily be outliers. We can, with fuzzy logic, say that if any one thing is a significant outlier, that's enough to make that entire event an outlier. Or if we can say there are many things that are somewhat outlying, that would definitely an outlier. Or if there's a lot of things that are a little outlying, that could be an outlier. So those are the fuzzy logic definitions, and we can summarize any of those statements from mathematical to an English language description. So that's why having a theory aids in explainability. I don't have to do a separate step to analyze. It's built into the math. And so that's the insurance example is quite difficult to capture. So let's talk about the retail example. In retail, we have fundamental truths about the halo effect. Customers who are buying a meal based on cereal, they're making breakfast for their children. So you buy cereal milk because you bought Cheerios, you bought a bit of sugar to sprinkle on the Cheerios because your kids don't like plain Cheerios. Or if you're doing my famous ground beef to make a pasta dinner, ground beef, pasta, tomato sauce, bread, wine, salad fixings, etc. So there's a halo effect. Because you bought Coca-Cola, you didn't buy Pepsi, there's cannibalization. Because it was on sale, you bought 4 weeks supply, there's pantry loading. And then the net effect of the halo is the positive impact of all the other items, plus the negative effect of cannibalization, plus the negative effect of pantry loading. That's the net halo. That's one fundamental truth. And on top of that is elasticity, because it was a low price. The lower the price, the more you bought, because it was a very prominent promotion. It was on the television ad and on the front page of your e-commerce site, very prominent. Your competitors had higher prices and not as visible promotions. That attracted people. So again, those are all the explainable facts based on the fundamental truths of the theory. And then we further say as an explanation is to say that this item that we're recommending is better than a previous one. We can say the difference between what you're doing today compared to a week ago, this item, ground beef, has a better net halo than doing steak, which you did last week. And it's a better time of year than steak. Steak is typically bought in the summertime, whereas ground beef is bought in the winter when you're making stews and pasta and things like that, whereas you're barbecuing steak, it's the wrong time of the year. And steak is a very expensive item. So even though you discount it, it's not very elastic, whereas ground beef is a lower cost protein, it's more elastic. So by comparing it to a less optimal decision, we're explaining the difference between worse decisions and better decisions in terms of those fundamental truths. And so that's an explanation that we can all understand. And because most of the retailers would agree with the fundamental truths, then that's something they can understand. And when you see the difference between what they did in the past that wasn't as effective, then that creates explainability, and it's built into the theory. A theory has these built-in factors. It's not a black box. To come up with the optimal combination of products is a complex mathematical exercise, but then explaining the individual elements of a set of decisions can be explained in terms of that fundamental truths and the difference compared to previous decisions you made. So that's explainability, and that will build trust. If the users understand this, they can see the explanation and they say, okay, I get that. That makes sense to me. And I think this theoretical approach has an advantage compared to the purely data-driven approach, which requires a separate step, requires you to address causality, whereas the theory, you're proposing causality. The theory is saying it's the net halo effect and elasticity, promotional price, seasonality. Those are the causal effects. And in insurance, it's the fact that it's an outlier with respect to its peers. That's the causal effect. So embedded into theory is causality. And then you can focus just on the causal variables. You don't need to go get all the data. You just need the data about the causal variables. Whereas in a data-driven approach, you've gotten some data. There's no guarantee that the data you have is the causality. And you're building a black box complex algorithmic model that is some complex mathematical formula, like a deep learning, reinforcement deep learning model could be billions of lines of mathematical equations, very complex to explain. If you explained the math, you'd have to have some different process to explain it, to simplify that. And again, because you don't necessarily have the causal variables in your data set, that creates complexity. So it's a more difficult, not saying it's impossible, but it's a more difficult task. So what should businesses do about explainability? I think this is a focus a lot of energy on that. And I guess there's maybe, a little bit of conversation about explainability. I think there needs to be a lot more. And I think this idea of having a causal theory approach, and I think every business people know the significant factors that affect the outcome of their business. Like, these aren't mysteries. So I think we need to infuse the data scientists with the business domain knowledge so that they can build mathematics in terms of the fundamental truths. Like, it's no mystery, what creates risk in banking. Like, your risk, if you have no credit history, that's unknown, you have an unknown risk. Or if you've previously defaulted on 10 bank loans, then you're highly risky. So we know this. I'm not saying data scientists don't know these things, but I mean, we need to make sure that the data scientists folks infuse those fundamental truths into their analytics so that we can have causality. And I think taking a more theoretical approach and coming up with a theoretical model, like in economics, there's more theoretical models. I think identifying a theoretical approach in any industry, identifying what the fundamental truths are that the business understands, and making sure we combine those things helps create explainability, because that'll create trust. When the senior executives see things they already know in a quantitative way, then that means they're more likely to believe it, adopt it, use it, whether it's senior management or any of the business users. So that's an important feature, explainability. Then going on to bias. So bias means, and I think this exists again in a data-driven approach. If you're building a model that is saying what are the past decisions I made, and building a model to say what correlates to past decisions, well, bias is the future to what you've done in the past. And if there's any implicit bias or unfairness in the past decisions, and there could be accidental unfairness because society in Canada was very ethnically different 30 years ago than it is today. You have an ethnic bias to the structure of society 30 years ago. So that could be carried forward to today's models if you're building credit approval models or insurance pricing models on the ethnic makeup of even 10 years ago compared to today. So you need to eliminate that bias so it's not unfair in the example of ethnicity or economic background or any other attributes, right? So you need to correct for any of those past decisions, and your business processes were different. The business was different. There could be all kinds of accidental biases created. Accidental bias, this is for fairness. There's also could be bias towards errors, right? So you could have made mistakes in the past, and you may be just reproducing those mistakes if you build models purely off the decisions you made in the past, because maybe you didn't know some fundamental truth about the business that you know today that you didn't know then, right? Or we didn't have e-commerce 20 years ago or maybe 30 years ago, and we have e-commerce today, that there's things we don't know. So there's a lack of knowledge. So we don't want to propagate mistakes into the future. We don't want to propagate accidental bias or fairness into the decisions we make. So how do we correct for that? And that's a difficult question. So that talks about how you sample the data from the past so that you're not biasing it, and how you mix it with more recent and current data and make sure you're not overweighting certain group of records or decisions. You're not, if in the case of customers, which is easy to understand, bias, that you're not having too many of a certain ethnic group in today's models, that you have a fair representation of every ethnicity so that you're not biasing against any one group or income strata or education strata or gender or anything like that. So it's how you carefully construct the data samples. Again, so that's complex. Now I say, are the laws of physics biased? No, because they're based on what we perceive as the fundamental truths in the laws of physics. So if you come up with a causal theory that's based on fundamental facts, like if you're saying, if you are an outlier with respect to your peers, is there any bias in that? The idea is no. Like if you're sick, if you go to the doctor and your measurements are sick, you have a higher blood pressure, you have a temperature, your symptoms, you're coughing and have a runny nose. Well, there's no bias in that. That's a fact. That's an objective fact. And when people have the objective fact of a fever, runny nose, cold, tired, and their medical measurements, their white blood cell count is high, and the peer to you has none of those measurements, you're an outlier with respect to your peers, it's a fact that you're different than the peers. And we know that if you're different than the peers and different than yourself in a baseline, you're likely sick. It's the illness that is some kind of illness that is causing those medical measurements. So there's no bias in that. So if we can have a fact-based, a theoretical approach, and similarly in retail, is there any bias that when you buy Cheerios, to make cereal, there's certain products you buy with cereal because that's what you use to consume cereal, and what every group of individuals does with a product is reflected in the purchases. There's no bias in those purchases. That's just a fact. The fact that in the winter time different things that are bought in the summertime, that's just a fact. When the price is lower, the fact that people buy more, there's no bias in any of those facts. So when you take a theoretical approach based on fundamental truths that have no bias in them, then there's less worry about implicit bias. I would argue almost no worry about bias, right? In that case. Whereas in the case of a data-driven approach, you must be very, very, very careful so that you're not biased. In the case of this theoretical approach, we are not using labels. There's no labeled past to create the future. So we're not biasing our decisions to the future. And this is what businesses need to work on. Who's the ownership of making sure that there's explainability and bias? And this goes into data governance. And I think all organizations need to have a data governance organization where the data science and analytics people are part of that. And we evaluate, ensure that in our business processes, we're not building any implicit bias or accidental bias into it. And this talks about the process of assembling data to build models. So it's a data governance organization and data stewardship. So in addition to just managing metadata and just managing data and collecting data and having a version of the truth, all the things you typically hear about in standard data governance, I think also because mathematics, even if you have a causal theory, there's data involved that you need, that this becomes part of the data governance or data stewardship, and an organization having that's responsible for all that. So I think this explainability and bias becomes a responsibility of the data governance organization, and then it needs to be infused into all the processes so that if you're doing mathematics and analytics, there needs to be some process to ensure that we're dealing with bias, dealing with explainability, that these are elements of all the initiatives and projects so that individuals don't accidentally build bias into the analytics they do. And I would say my guess would be that this is still in its infancy in organizations today. That I think there's a lot of analytics people building models today. Vast majority of people have no malintent and don't want to create bias. But again, it's not a simple thing to eliminate. So I think that's why it's important to have these stewardship. And typically this would be under the guise of information technology and business. It needs to be collaboration between those two areas to manage this explainability and bias. So hopefully that sheds some light on explainability and bias and what we think about, and some of the reasons why DAISY has chosen its mathematical approaches because of some of the benefits in explainability and bias that help us succeed with our clients today. As always, follow us on Spotify, on YouTube. Feel free to ask any questions. Feel free to disagree. Send your comments. Would welcome those, and love to follow up and chat with anybody interested in having a further conversation.